Reading the status of a push button or other on-off input can be problematic in any but the simplest Pico W program. If you use an if statement, such as if red button value equals 1, you may completely miss changes in button status if the Pico W happens to be executing a different part of the program when the change occurs, especially if the change is transient. You might also try the while loop shown here. This logic will certainly catch the change in button status, but the program will come to a complete halt waiting for the button to change status. Nothing else will get done. Using the other core to capture button value changes will work for a single button, but you'll be faced with the same problems if you have multiple buttons to capture, or you also need to use the other core for anything else. Plus, it also seems to be a waste of horsepower to use the other core this way. In Lesson 83, Paul explained that hardware interrupts are the solution to the problems described on the previous screen. Hardware interrupts are very similar to the timers we learned about in the last 3 lessons, but instead of triggering on time, they trigger on a rising or a falling hardware or GPIO change. Similar to the timer, once a hardware interrupt is triggered, it calls a user-defined function which runs with minimal impact on the main loop. Hardware interrupts have 2 parts: the interrupt request, or IRQ, and the user-defined interrupt service routine, or ISR. The IRQ declaration has 2 parameters: a trigger, which is a set of rules that control when the request is raised, and a handler, which names the ISR function which will be called whenever the IRQ is raised. When the trigger rules are satisfied, the Pico W will raise the interrupt request, stop the main while true loop, and record the program status so that it can resume from where it was interrupted once the ISR is complete, call the interrupt service routine, named in the handler parameter, and resume the while true loop from where it was interrupted when the ISR is complete. Notice that the ISR doesn't really run in the background. It runs while the main while true loop is stopped. So it's important to keep the ISR as short and single-purposed as possible in order to minimize that stoppage. Paul also introduced the issue of switch bounce in Lesson 83. Electrical switches often contain miniature spring metal components which help to close or open the switch contacts as quickly as possible. From time to time, the contacts will close with such force that they momentarily bounce open before finally closing. As you can see on the oscilloscope trace, this is a very fast movement. Fast or not, these signals can be captured by the hardware interrupt and misinterpreted as multiple key presses. Switches can also bounce when they open. Our ISR code must be designed so that it does not misinterpret switch bounce as multiple button presses or releases. Below we see a timeline showing the status of a push button over time. We can see that after opening at A and sitting untouched for a period of time, the push button is pushed at B. The button closes, but bounces open momentarily before closing at C, only to bounce open again before it finally closes at D. Intuitively, we can pick out the bouncing behavior. Writing code to identify bouncing takes a little thought. The button press at B occurs a relatively long time after the most recent button release at A. Let's call that time duration 1. By comparison, the switch closure at C occurs much sooner after its previous switch opening. Let's call that duration 2. The closure at D occurs relatively soon after its previous switch opening. Let's call that duration 3. So the time between a switch closing and the previous opening can be an indicator of a real button press. Let's see what happens when we release the button. The button is released at E. It opens, but bounces closed momentarily at F, and briefly again at G before remaining open. In this case, we can see that the time between a switch opening and the previous closing can be an indicator of a real button release. We'll configure the IRQ so that it calls the ISR whenever we have a rising or a falling signal. The logic will prove rising signals are a valid button press by comparing the time of the closing with the time of the previous opening. The logic will also prove that falling signals are a valid button release by comparing the time of the opening with the time of the previous closing. Our Lesson 83 assignment was to use a hardware interrupt to capture the status of a push button and to configure the ISR so that it would ignore switch bounce for rapid presses, slow presses, sloppy presses, etc. An extensive demonstration was required. Lesson 84 and 85 are meant to demonstrate our understanding of hardware interrupts. We're required to create a 4-bit up counter in Lesson 84 and a 4-bit up-down counter in Lesson 85. Let's start with a look at the code for Lesson 83. We're going to be interfacing push buttons, so we need to import pin. We're going to be using time.ticks, so we need to import time. Here we declare the GPIO pin for the red button, and then declare the red button object. And here we declare a few variables used in the program. At this point, we declare the red button ISR. After declaring our global variables, we capture redButton.value in a variable. If red button value is 1 and the previous red button value is 0, we may have a new button press or a bounce on our hands. As described earlier, we compare the time of the so-called red button press to the previous red release time. If the difference is 25 milliseconds or more, we declare the press to be real. Increment our press counter, print count in the shell, and update previous red press time. If red button value is 0 and the previous red button value is 1, we may have a new button release or a bounce on our hands. As described earlier, we compare the time of the so-called red button release to the previous red press time. If the difference is 25 milliseconds or more, we declare the release to be real and update previous red release time. In either case, we update previous red button value so that it will be available next time the red button ISR is called. In line 35, we declare the red button IRQ. We specify that the red button ISR function will be the handler for this IRQ, and we specify that it will be called when red button value is rising or falling. Finally, we have the expected try except clause. The while true loop is empty, and the except clause will exit cleanly if the user presses Ctrl-C. And here's how it looks. Now that we know we're not being fooled by switch bouncing, let's look at the code for the up-down counter. The up-down counter is based on the Lesson 83 code. I'll just highlight the differences here. We declare additional GPIO pins and objects to accommodate the 4 LEDs and the additional push button. We also need additional variables to track the status of the green push button. The F string in the display count function converts the count variable into a 6-position binary formatted string as shown here. The integer values of bits 2 through 5 in that binary string are used to drive the LEDs. The up-down counter has a hardware interrupt for each button. The ISR logic is basically the same as in Lesson 83, except that the red button increases count and the green button decreases count. Also, we roll the count over at 15 or -1, and we do not print the count in the shell. Rather, we pass it to the display count function, which displays it on the LEDs as described earlier. The red and green IRQ declarations follow the same pattern as the IRQ in Lesson 83. And this keyboard interrupt turns the LEDs off before declaring that the program is finished. And here's how it looks. Well, that's it for this assignment. Any and all comments are welcome. Don't forget to like or dislike the video before you go. And feel free to subscribe. Don't forget the notification bell. We'll talk to you next time.